In this video, we will continue that topic, that is evaluation of improper integrals. We have been discussing that topic in our last two videos. The first was when we evaluated an improper integral of the form minus infinity to infinity with a rational function as an integrand. And in the second case, we discussed when again the limits were from minus infinity to infinity, but the with that rational function we have that exponential function multiplied with it, right? Or you can say that fx cos ax dx form, right? In this video we'll continue the topic, but with an extra case when the poles of that function, rational function, lie on real axis, right? So I will recall what we have done so far in the last two videos. Okay, so far we evaluated this kind of integration minus infinity to infinity, and we had fx over gx, or I think px over qx, px over qx dx, this integral, right? And minus infinity to infinity, px over qx e to the power eta ax dx, right? So we have evaluated these two type of integrals with the help of residue theory, right? And in both of these cases we have seen that the poles of the corresponding complex function, right, were either on the upper half plane or lower half plane, and we are not interested in the poles which lie in the lower half plane. Rather we take a big semicircle that lies in the upper half plane with the radius bigger enough to enclose all the poles which lie in the upper half plane, right? So we have a contour in both these cases, a semicircular contour together with the diameter, right? And none of the poles of these functions were lying on the real axis, right? So what happens when the poles of this rational function lie on a real axis, right? Since our contour is of this form, interval minus r to r, and this anti-clockwise semicircular arc, and we have to trace over that real axis, right? And what happens when the one or more poles lie on the real axis, right? The point is that the contour cannot pass through a pole, right? You have to make a small indentation there or small jump at that pole, right? I will draw the figure. So far we have our contour of this nature, minus r to r, and then a semicircle, big semicircle, right? And it's called CR, right? In this video we will be looking at the examples when one or more poles lie here on a real axis, right? In that case, since our contour is this, right, consisting of this interval from minus r to r and the semicircular arc, we cannot go through this pole. We have to avoid this pole, right? It is like a pole is like a misfortune. You cannot just go through the pole. You have to make a small jump here, like this, a small jump, right? So this will create a small semicircle here at this point, right? And it should be as small as you please. Means the radius should be very, very small, right? So I will I will draw the contour. This is the specially designed contour when one pole, I will name it z equal to k. This is z equal to k, or I should make it big in order to that you can visualize it. Okay, right. So this is your pole lying on the real axis, and what we have done, the semicircular arc is intact, but while traveling along this real axis you made a small jump, right? And there is a semicircular arc, and this is called CR, right? Because the radius of this semicircle is a small r. So this is a pole, z equal to k is a pole. So this point will be I think k plus r, right? K plus r, and this point will be k minus r, right? And I will make it big. Here you have your r, and this is the minus r, right? Okay, fine. Now it will be visible. right? This is your y-axis, this is your x-axis. This is your C capital R, this is your C small r, right? And now you have the whole contour is called C, right? I have made only one pole. There may be more than one poles on real axis. In that case, you have to do indenting. That is called indenting. Means you are avoiding a pole. You are avoiding to cross a pole. You are making a semicircular arc, a small jump at that pole, right? In order to avoid that pole in your path. Okay. So for this case, when the poles lie on real axis, the contour looks like this, right? Okay. We evaluated this, and none of the poles lie on real axis so far, right? So in this lecture, what happens when a pole, I am taking just a pole, z equal to k, lie on a real axis, right? So you can refer to the figure. So this is the question. What happens when a pole z equal to k lie on x-axis, just like this, right? So in that case, what we do, we just avoid that pole, right? We make a small jump at that point with a very small semicircle, and that radius of that semicircle is very small, that is denoted by small r. So if this is the center of the semicircle, this point should be k plus r, and this should be k minus r, right? And now the contour looks like this, right? First I will start from here, the big semicircular arc, right? Bigger enough to enclose all the poles that lie here in this region, right? And then this minus r to k minus r, this is the real interval, and then the semicircular arc, this is clockwise direction, small cr, and then k plus r to r on real axis, right? So this will be our contour. Okay, so we'll apply Cauchy Residue theorem here, and if you see the figure, you can see that we will consider the corresponding complex integral, just like as we have been doing before. Consider I is equal to the corresponding integral for this or this, that will be if I say p z over q z, or should I write it at fz, right? Fz, f z d z, where c is as shown in figure, right? C is just a big semicircle CR, and then minus r to k minus r, and then this small semicircle, then k plus r to r, right? Okay, then from figure it is clear that the complex integral should be equal to, the first is this thing CR, and there is f z d z, then this part, right? Minus r to k minus r, it is on real axis, minus capital R to k minus small r, and since it is a real axis, so I will write fx dx, right? And then this semicircular arc, and you see that the direction of this semicircular arc is clockwise, right? And that is taken negative, right? So I will put a negative sign here, and we'll write c small r here, right? Okay, and then f z d z, and then again this k plus r to r plus k plus r to capital R fx dx, right? Okay, now again using that Jordan's lemma or estimation rule, when this function is of form pz over qz, right? We can use Jordan's lemma here if exponential function is present beside it, right? So this will go to 0. You should know the reason why I am writing it. We have done it in our last two videos, right? 0 by Jordan's lemma. Jordan's lemma. If this fz is of the form e to the power iota az multiplied by pz over qz, right? Or we apply here maximum value, or taking maximum value, or upper bound, you say it upper bound, right? Maximum value. when this is of rational form, right? Okay, so this goes to 0, and yes, we are left with this thing. Okay, then we apply capital R tends to infinity and small r tends to 0 here, as capital R tends to infinity and small r tends to 0. Since you know that this semicircle should be large enough to enclose all the poles which lie in the upper half plane, and this small semicircle should be smaller enough, right, in order to just avoid this pole k, right? So small r should be almost equal to 0. Okay, so approaching these limits here, I will get I think this will be, and its value will be 2 pi eta multiplied by sum of residues, right? And residues calculated at poles which lie in this region. This is very important point. To evaluate this integral, this one, right, you should notice that your C is actually this thing, this path, this is the complete C, right? And this C is enclosing this region, right? I am putting dots here. So any pole that will lie in this region, let it be Z1, Z2 up to Zk, right? At all of these poles which lie in this shaded region, a residue will be evaluated and then multiplied by 2 pi eta in order to find the value of this integral, right? Now do not use this pole, right? This pole is not belonging to the shaded region, right? So only take these poles which lie in the shaded region. I will write that. Then it will become 2 pi eta times the summation of residues of function fz evaluated at z equal to zi, and I starts from 1 to k. You can see that this is z1, this pole is z2, and finally it is zk, right? I to k, okay, equal to, and since this is 0, we'll have minus infinity. I think principal value should be written there, minus infinity to, it will become k, right, k, and minus limit r tends to 0, cr fz dz plus k to infinity fx dx. I should write here fx dx, right? And this integral will go on the same side with this, and if you see these two integrals, they will be minus infinity to infinity, right? So ultimately we'll be having, on summing these two integrals, we will be having minus infinity to infinity, but we should write principal value, right? And then fx dx equal to, I think, limit r tends to 0, cr fz dz plus 2 pi eta summation I equal to 1 to k residue fz z equal to z eta, right? So ultimately we have this expression for the value of the integral, right? And what about this residue of fz? Okay, this is known, fine, sorry. What about this, the value of the integral along this small semicircle, right? Actually the value of this thing is or principal value of minus infinity to infinity fx dx equal to this, its value is pi eta multiplied by residue of fz evaluated at z equal to k, right? The value of this integral is equal to pi eta times, why pi eta? Okay, you can think like that because it's a semicircle, right? So you should multiply it by pi eta, right? Had it been a full circle, then 2 pi eta. So pi eta multiplied by residue evaluated at the only pole that is enclosed by this semicircle. You can see that this k, right? And plus 2 pi eta summation I equal to 1 to k residue of fz evaluated at z equal to z eta, right? Okay, so ultimately you will be using this formula, right? And I will give a proof for this, why the value of this integral is equal to that much, right? We have a small proof for it as proof of this, proof of this thing, limit r tends to 0 cr fz dz is equal to pi eta times residue of fz evaluated at z equal to k, right? So proof goes like this. Since fz has a simple pole at, or I assume that let fz has a simple pole at z equal to k, right? Okay. Then fz can be written as a minus 1 over z minus k plus gz, right? Since you are saying that fz has a simple pole at z equal to k, so fz can be expressed as a Lorentz series where the highest negative power of z minus k should be minus 1, right? And this is called the principal part, because we know that when we have a simple pole at some point z equal to z naught, then the principal part of a Lorentz series contains only finite terms, right? And if it is a simple pole, then the highest negative power of z minus z naught should be minus 1, right? Okay, and this is called analytic part. For Lorentz series, we have two parts. The first one is principal part and the analytic part. So this is this gz is actually containing all the non-negative powers of z minus k. I am not writing in expanded form. Actually, it should be a naught plus a1 times z minus k plus a2 times z minus k whole square and so on. Means all non-negative powers of gz, right? I will write that here. And yeah, because the Lorentz series is important, I mean it gives the correct information if and only if you should you should choose the correct domain, right? So I will mention the domain here. In the domain should be like that, it should enclose only that singularity. Means if you are expanding in powers of z minus k, then your domain should be enclosing just z equal to k pole, right? So the domain should be like this. The center is k mod z minus k, and it should be greater than 0 obviously, right? And I think it less than capital R. Okay, fine. Or should I rename it, because capital R is used here? Okay, it should be I will name it R1, right? Okay, where gz is analytic, right? Okay, then I will perform integration on both sides because I need this value. There is that, this one, limit r tends to 0 cr fz dz. So I will integrate this both sides, right? This will give me on integration fz dz over the contour cr, right? And since it is a constant, a minus 1 will come outside, so dz over z minus k evaluated along the contour cr, right? And plus integral gz dz, right? cr. Okay, and to evaluate this I will use parametrization, since I know that cr is actually a semicircle, right? Use parametrization, right? And that should be z minus k equal to e to the power eta theta, because this equation of the circle is like this, right? K is the center, you can see that, and radius is equal to, sorry, r, small r should be here, radius is equal to small r for this small semicircle, right? And theta varies from, you can see that theta varies from actually pi to 0, because we are tracing this semicircle in reverse direction, right? But since where is that term? Originally this term was occurring here, right? And I have considered minus sign already, means I have considered this minus sign, and this minus sign was due to the angle pi to 0. So I have already considered this negative sign, means I have already considered the angle pi to 0. So here I will write 0 to pi, right? Because negative sign is also taken into account, right? Where theta varies from 0 to pi, 0 to pi, okay. And on differentiating it, I will get dz equal to r e to the power iota d theta, okay. And the value of this thing will be integral CR fz, or should I evaluate these two separately? I should call it equation number 1, okay. And now integral CR dz over z minus k will be equal to, using this parameterization, r e to the power iota d theta, right, over z minus k is actually equal to r e to the power iota theta, okay. And limits of theta are 0 to pi, and then it will be cancelled, iota will appear outside, and ultimately we'll get iota pi, right, or pi iota, okay. And what about this? And since gz is analytic, so it must be bounded on CR, right? Since you know that your gz, this is an analytic function, this is a analytic part of this Lorentz series, it will contain all the non-negative powers of z minus z naught, right? So since it is an analytic function on this boundary, so it must be bounded, right? And let that bound be, that is, let that bound be denoted by, let me denote it by a small mr, right? Okay, fine. Then plugging this value here in the second integral, that is CR gz dz, I will take the maximum value of this thing, right? And this will be lesser than or equal to integral CR mod of gz dz, and you are replacing this gz by small r, right? That will give you a small r, and integration c along CR of dz, that will be actually equal to the length of this semicircle, and that is equal to the perimeter of the semicircle pi r, right? Pi r, and this r is at its subscript, right? mr, right? And yeah, okay. Then plugging these values in equation number 1, put in equation number 1, I will get integral CR fz dz equal to a minus 1 multiplied by the value of this thing, and that is equal to pi iota, and this is mr pi r, right? And since as r tends to 0, I will apply limit r tends to 0, it will give me limit r tends to 0 CR fz dz, and this is actually a minus 1 is the coefficient of 1 over z minus k, and that coefficient has a special name that's called residue, right? So I will write in place of a minus 1 residue, so it will become equal to pi iota times residue of fz evaluated at the pole z equal to k, and this will go to 0. If you approach r to 0, this will go to 0, right? So ultimately you have proved this result, right? So it is a small proof for this result. We will be using this result directly in place of the value of the integral along this semicircle. We will use the value directly, and that value is pi iota times the residue of function evaluated at that particular pole that is lying on x-axis, right? And if there are more than one poles lying on x-axis, suppose we have a pole here, then we will make another circle here, or indenting at that point, that is called indentation, right? Okay, at that point also, and then we will find this residue twice, one at the pole z equal to let it be k1 here, and another will be z equal to k2 here, right? Okay, so I will take numericals of this thing. Taking first example, find the value of integral 0 to infinity sine mx over x dx, right? And where m is greater than 0, right? So we see that we have this function sine function here, and we'll replace this function by an exponential function, right? So I will start with the corresponding complex integral, and that should contain this e to the power iota mz here in the numerator, right? And you should know the reason why, because the imaginary part of this function will be this thing, right? Okay, over z dz, and where c is as shown in figure, right? And remember that our c will be that semicircle, big semicircle together with the diameter, right? But this time we have a pole z equal to 0 on our diameter, so be careful at this point. The contour will look like this. You should make a small jump here at z equal to 0, right? Okay, y-axis, and this is x-axis. This is z equal to 0. This is your pole which lies on the real axis, and due to which you have done this indentation, right? A small jump. And I think it should be minus r, it should be plus r, 0 minus r, 0 plus r, right? And the right end and left end are capital R, and this should be minus r, right? And this is C capital R, and this small semicircle is C small r, right? So the figure should look like this. And since you see that there are no poles here inside your C, right? This is your C, this is your C, right? And here we have no poles. The only pole is z equal to 0, which lies on x-axis, and I have done indenting at that point, right? Okay. Clearly, z equal to 0 is a simple pole on real axis, and that's why we have done indenting at that point, right? Now I will use that breaking of integrals, that is I is equal to, this is I, or I can write it at I e to the power times z dz equal to the first one is this bigger semicircle, and we have fz. What is the fz? This is my fz, or should I write it as e to the power iota mz over z dz? Then we have this thing minus r to minus r, and then we have e to the power iota mx over x dx. And then we have this smaller semicircle, but it is placed in negative direction, so I will put a minus here, and this is c small r, and e to the power iota mz over z dz. Then we have this r to r, right? R to capital R, e to the power iota mz over z dz, right? And this integral will go to 0 by, I will use Jordan's lemma, right? And the value of this will be 0, right? This is an important point. You see this is C, this is C, right? It is not enclosing any singularity. You can see that this shaded region is not enclosing any pole or any singularity, so the value of this will be 0. It means that this function is analytic over this region, right? The value of this integral will be 0, right? So I will write 0 here. This will be 0, right? By Cauchy Residue theorem, you can say that, because the function is analytic over this whole shaded region, the value is 0, and this will go to 0, right? I will explain that why it goes to 0 by Jordan's lemma, right? We'll do that here, and yeah, the rest of the integrals will be like this: minus r to minus r e to the power iota mx and x dx. I think I should take this integral here, right? Okay, I'll leave that, plus r to r e to the power iota mz z dz, right? And finally, on applying, r tends to infinity and small r tends to infinity, small r tends to 0, as capital R tends to infinity and small r tends to 0. These two integrals will be added up to give principal value of minus infinity to infinity, because the minus infinity is 0, 0 to infinity, e to the power, I think it should be r to r x it should be minus infinity to infinity e to the power iota mx over x dx, right? And where is that? This one, minus cr, its value is pi iota, pi iota multiplied by residue, I should write it here, minus pi iota, the value of this thing, pi iota minus multiplied by residue of fz, your function is fz, this is fz, e to the power iota mz over z evaluated at z equal to 0. I will evaluate that, right? So ultimately this will go to the right hand side, pi iota multiplied by residue of the function e to the power iota mz over z at z equal to 0, right? Okay. And if I calculate the residue of this function at z equal to 0, you can see that z equal to 0 is a simple pole of this function. So I will use that formula, derivative formula, e to the power iota m times 0, and the differentiation of the denominator is 1, right? So ultimately we will be left with pi iota, right? And the explanation for this thing, I will put a star here, by Jordan's lemma. I am giving a small proof why it becomes 0 using Jordan's lemma. However, we have done that in our previous video in detail. So the proof of this integral going to 0 is like that. Since see the companion function, the companion function is the function present beside this exponential function, that is 1 over z, right? And you see that the m, we denote that by mr, right? Mr equal to maximum value of that rational function present with this exponential function, that is 1 over z, on this bigger contour, bigger semicircle CR, right? On CR, right? And that should be equal to is equal to, I think, 1 over r, right? You can see that if you take the modulus of this thing, right, you will get 1 over r. Okay. Okay, then equal to 1 over r using Jordan's lemma. We have that integral limit r, no, not Jordan's lemma, limit, not limit here, CR, here we have e to the power iota mz over z dz is equal to, we have that formula, pi multiplied by that maximum value over small a, and this small a is actually this coefficient of iota z, this is m, right? And putting the value of mr, that will give me pi over rm, right? So it will approach to 0 as r tends to infinity, right? So ultimately this value is 0, that's why we have used this 0 here. So for this star, this is the explanation, right? This is the explanation for this star. Okay, and now I will proceed from here, equating real and imaginary part. I will use cos mx plus iota sin mx, right? So that will give me principal value minus infinity to infinity. I am equating the imaginary part only, right, over x dx and equal to pi iota, right? Equate imaginary parts, you will get sin mx over x integral minus infinity to infinity, principal value is also there, dx is equal to pi, right? And since this is an even function, sin is an odd function, x is an odd function, so ultimately if you replace x by minus x, you will get the same function. So I can write that this principal value is actually equal to the value of the original integral, right? Or the original integral should be equal to, here we have mx is equal to pi, as sine mx over x is an even function, right? Note that you can only replace the principal value of an integral by its actual value if and only if the function is an even function, right? And since again this function is an even function, I can use that twice property, twice of 0 to infinity, right? Or integral 0 to infinity sine mx over x dx equal to pi by 2, right? Again the reason is same, it is an even function, right? So the value of this integral is pi over 2. And taking another example, example number 2, find the value of integral 0 to infinity cos twice of ax minus cos twice of bx over x square dx, right? Where we have a is greater than or equal to b, right? Again we have cos functions in the numerator, but this time we have 2 cos, right? So I will write it as a real part of e to the power eta 2x and minus eta 2b x, right? So I will start with the exponential function, just like to this solution. Consider I equal to complex integral, and that should be e to the power eta 2az for this thing minus e to the power eta 2bz over z square dz, and where c is as shown, right? And again this time you can see that you have this pose z equal to 0 is a singularity. If you focus on the denominator only, you will get z equal to 0. Again that z equal to 0 will lie on real axis, and there is no other singularity, right? So the figure will be same. Okay, I'll draw the figure, the small figure here. This is a bigger semicircle CR, and here we have capital R, here we have minus R, and okay, this is a small semicircle. You have done indenting at this point. This point is z equal to 0. This should be 0 plus R. This should be 0 minus R, right? And the direction is clockwise. Okay. And in this shaded region, there is no pole, right? This y-axis is x-axis. Okay. So first, I will break the integral into 2 or 3 parts, 4 parts, as I is equal to, the first should be this one, CR e to the power eta 2a z minus e to the power eta 2b z over z square dz, then plus minus r to minus r, it is on real axis. So I will write e to the power eta 2a x minus e to the power minus 2 eta 2 bx over x square dx, then this smaller semicircle with the negative direction, so I will write minus here and write CR e to the power eta 2a z e to the power eta 2b z over z square dz, and then this last part r to r plus r to r e to the power eta 2ax minus e to the power eta, this plus eta 2bx over x square dx, right? And this will go to 0, right, by Jordan's lemma. Jordan's lemma, you will show it by yourself. And yes, as, and the value of this thing, capital I is actually equal to 2 pi eta multiplied by sum of residues at poles which belong to this shaded region, but there are no poles in the shaded region, so ultimately the value of this integral will be equal to 0. So you should know the region y, right? Equal to, this is actually equal to 0. Okay, and this will give you plus minus r to minus r e to the iota 2x minus e to the power iota 2bx over, as r, I should write here as r tends to infinity, I will write it here as small r tends to 0 and r tends to infinity. So it will become, ultimately it will become minus infinity to plus infinity, right? Minus infinity to 0 and 0 to infinity. On adding we will get this thing. I should write principal value here, 0 plus principal value x square dx. And what about this thing? This is actually equal to minus pi iota residue of function. What is my function? My function is this whole function, right? I am writing it as fz. Okay, so treat this function as fz, right? Fz, and the residue is evaluated at z equal to 0, right? Okay, and then finally it will become or principal value of minus infinity to infinity e to the power iota 2ax minus e to the power iota 2bx over x square dx. This will go on the other side and that will give you pi iota, and you should calculate the residue at z equal to 0. And where is that function? Okay, this is my function, right? And it appears that z equal to 0 is a pole of order 2, but that's completely wrong. You notice that if you equate your denominator to 0, that will give you z equal to 0 0 twice, right? But z equal to 0 is also 0 of the numerator function. If you put z equal to 0 here, you are getting numerator 0. So be careful at this point. Z equal to 0 is a pole of order 1, not of order 2, and that fact will be supported if I allow me to expand this exponential function. I will get only 1 by z coefficient. So this time I will write coefficient in place of residue. I know that residue is actually equal to coefficient of 1 by z in expansion of, right, in expansion of function, and the function is fz. I have treated this function as z, right? I am using the original definition to find the residue, right? And then I will expand this function. That will give me pi iota times, if I expand this I will get 1 over z square, and that should be equal to 1 plus 2a iota z plus so on. I need not to write the whole series, right, because I have already got 1 over z here, right? And for the second one, 1 over z square is outside, okay, bracket, minus 1 plus 2b iota z and dash dash, right? So you can see that the coefficient of 1 by z will be 2a iota minus 2b iota, right, equal to pi iota 2a iota minus 2b iota, and on multiplying iota inside I will get and this sign will be reversed, 2 pi b minus a, right? So ultimately the principal value of this function is this much, right? And this time I have used the original definition of residue. There is a coefficient of 1 over z minus z naught in the Lorentz expansion, right? Okay, and now since a principal value of this thing, I need cos, so I will equate the real parts, equate real parts only, and the real part of this will be cos 2ax, and real part of this will be cos 2bx over x square is there, dx, and minus infinity to infinity, and principal value is also there, right, is equal to twice of pi b minus a, right? And since it is an even function, you can see that cos is an even function, x square is also even. So ultimately for an even function we can replace this principal value by the original value of the integral, and that will give me integral minus infinity to infinity cos ax minus cos bx over x square dx equal to this will give you 2 pi b minus a, right? And since it is an even function, we can again use that property, twice 0 to infinity, and that 2 will be cancelled by this thing, right? So this is the final value of the integral, right? Okay, so far we have done 2 examples. In both cases this shaded region was not enclosing any singularity, right? So in third example I will take the denominator such that one or more poles will lie in this shaded region, right? In both of these 2 examples we have got this I is equal to 0 in both of these, right? So taking another example of different type. Example number 3, find integral finds infinity to infinity sin x over x square minus 2x plus 2 dx, right? Okay, so you can see that this time again we have this sine function here. I will replace this by e to the power iota z. Solution: consider integral I equal to c e to the power iota z over z square minus 2z plus 2 dz, where c is as shown in figure, right? And this is my figure. There's a big semicircular arc here and C capital R, right? And since you can see that this is z equal to 0 is a pole again at origin, okay? So I will put a small semicircle here, C small r, and this is 0. So the right hand side should be 0 plus a small r, and it should be 0 minus small r, right? And this is capital R, this is minus capital R, okay? And yes, this shaded region, this time this region, shaded region, is containing one, I think one pole, yeah, that will be given by this thing. If you equate this equal to 0, you will get 2 plus minus 4 minus 8, that will be ultimately 2, okay, that will be cancelled. So 1 plus minus iota, I think 1 plus minus iota, yeah, 1 plus minus iota, and 1 plus iota will lie here, 1 plus iota will lie here. I will put a big dot here, 1 plus iota, right? And 1 minus iota will be on the fourth quadrant, but that is not inside our domain, right? So this time our C, this is my C, this curve contour is C, and it is enclosing one pole this time, right? And another pole is on the real axis, right? So we have two poles in all. One is inside our region, right? And another pole will be a pole on real axis, right? So that should be given a special treatment, right? Okay, so from figure I will start. First I should evaluate the value of this I, right? And since z equal to 1 plus iota is a simple pole lying inside the shaded region, that is C, right? So finding a residue at z equal to 1 plus iota for this function, since it is a simple pole, should I use a differentiation? Okay, e to the power iota z, and I think that should be z multiplied by z minus 1 minus iota, and another should be z minus 1 plus iota, if I am not wrong, and it should be like this, z minus 1 minus iota and e to the power iota z, okay, and then we put limit z tends to 1 plus iota, right? So ultimately these two factors will be cancelled out, and I will be left with e to the power iota 1 plus iota over 1 plus iota, and this will be 0, this, okay, this is cancelled out. 1 plus iota plugging here, I will get 2 iota, yeah, 2 iota, and on simplifying it I will get e to the power minus 1, yeah, iota square minus 1, and iota, e to the power iota cos 1 plus iota sin 1, right? Okay, cos 1 plus iota sin 1, and here, okay, this is also 1 plus iota, so iota should be multiplied inside, and I will get iota minus 1, right? Should I rationalize with the opposite sign, because I have to multiply it by 2 pi iota also, right? So if I, okay, leave it, I think we should leave it here, because in that case it will be cancelled. Leave it here only, or we should just rationalize it by 1 minus iota. If I rationalize this by 1 minus iota, I will get 1 minus iota in the numerator, right? And I think it will become 1 minus iota square 2, it will become 4 iota, 4 iota. So ultimately our residue will be this thing, right? So therefore the value of I is equal to the integral evaluated along the full contour C dz should be equal to 2 pi iota times this residue, and that will give you 1 minus iota e to the power minus 1 plus iota over 4 iota. So ultimately that will produce pi by 2 and 1 minus iota minus 1 plus iota, right? And remember that actually this function has poles at 0 and 1 plus iota and 1 minus iota, right? This pole z equal to 0 will be treated, is not belonging to C, note that, right? This z equal to 0 is a pole, is not belonging to C. You can see that from figure, right? Okay. So that's why we have evaluated the value of the integral by multiplying 2 pi iota, multiplied the residue only evaluated at this one pole. Out of 3 poles, only one pole is qualifying, right? Okay. Now breaking that integral from figure, you can write that the value of the integral I, that is equal to pi by 2 1 minus iota, and it should be e to the power minus 1 plus iota, e to the power minus 1 plus iota. Okay, e to the power minus 1 plus iota, and then equal to first will be CR, and the integral is, I should write it as fz only. This is fz, right? The whole function is fz plus minus r to small minus r and fx dx, and then the semicircular contour small cr fz dz, and the last interval r to r fx dx, right? And as small r tends to 0 and capital R tends to infinity, this value will be there, this will go to 0, and these two will be added up, right, to give minus infinity to infinity, and it has value pi iota times the residue of fz evaluated at 0, right? So I will write that and take this value here on the same side. So ultimately I will be having principal value minus infinity to infinity of fx dx equal to pi by 2 1 minus iota and e to the power minus 1 plus iota plus pi iota, this is the value of this thing, pi iota, and residue of fz evaluated at 0, right? So all I need to evaluate this residue, the residue of the function, evaluate where is my function, this is fz, right? This is fz, and the residue is evaluated at z equal to 0. So that is easy. I think that will be e to the power 0 is 1 by 2. Or should I write that directly? That will be pi by 2 1 minus iota e to the power minus 1 plus iota. I think it should be pi iota times 1 by 2, right? If you evaluate the residue at z equal to 0, 0, 1, 2, yeah. And now I will, I think what is sin x, okay. Okay, I will write the principal value. I will liquidate the imaginary and real part first. So I'm taking imaginary parts. From left hand side I will get principal value of integral minus infinity to infinity. I think fx should be e to the power iota x, and its imaginary part will be sin x, right? And x over x square minus 2x plus 2, right, dx, right, equal to imaginary part, taking imaginary part, that is equal to, if I write it as e to the power minus 1, e to the power iota is cos 1 plus iota sin 1, and I need only imaginary part. So it will be, first will be e to the power minus 1 will be there, okay, pi by 2 e to the power minus 1 and 1 minus iota multiplied by cos 1 plus iota sin 1, and on equating imaginary part, right, I will be having only One term will be sine eta, sine 1, sine 1 with this, and minus cos 1, right? Sine 1 minus cos 1, okay. Sine 1 minus cos 1, right? So this is the principal value of this function, and yeah, it is not an even function, you will see that due to this x, right? So the question should be principal value, right? Okay. So this is the answer, right? I need minus infinity to infinity. It cannot be extended further because this is not an even function, right? So this is the value of the integral. Okay. And yeah, one more thing, this is pi by 2, so pi by 2 will be added up, and should I take the common, pi by 2 plus 1, right? So this will be the final value of the integral, right? And now taking another example, example number 4, find integral minus infinity to infinity x cos x and x square minus 3x plus 2, right? And again I should write principal value here because this is not an even function, right? It is just an ordinary function, so principal value will be there. And yes, this time I am having x square minus 3x plus 2. It will give two poles rather than having one pole as we did in our 3 examples, only one pole on real axis, but this time I will be having two poles, right? It will give 1 and 2. Okay. Solution: consider the corresponding complex integral that should be z e to the power eta z. So I should write it as real part of, or should z to the power e to the power eta z. Okay, fine. And z square minus 3z plus 2 dz, where c is as shown in figure, right? And before actually drawing the figure, you should first find its poles. Its poles will be 1 and 2, right? So you already know that its poles are 1 and 2, that both lie on real axis. So I will draw the figure like this, big semicircle, and we have two poles, there is 1 and 2 both on this side. Okay, so one pole is here. I will make a bigger picture, right? Bigger on the right hand side, like this one. Okay, now it is visible. Y-axis and x-axis. So one pole is here, z equal to 1, and one pole is at z equal to 2. This is capital R, this is minus R, this is C capital R, right? So I have to do indenting at 2 points. One is at the pole z equal to 1, right? And another indenting at z equal to 2. Okay. So there will be two semicircles like this. This is CR1, this is CR2, right? Its radius is small r, and the another one having radius is small r2, right? So if this is 1 and radius is small r1, the right hand point should be 1 plus r1, and the left hand of diameter is 1 minus r1. Similarly for this, 2 plus r2, and here we will have 2 minus r2, right? Where r1 and r2 are very small, and there are no other poles, right? Means that this shaded region is containing no singularity, right? Okay. So this time our contour is this, the bigger semicircular arc CR, then the part of real axis from minus R to 1 minus R1, then this smaller semicircular arc CR1, again this part of real interval 1 plus R1 to 2 minus R2, and then this again this semicircular arc CR2, and the last 2 plus R2 to R, right? Okay, so writing this fz as I equal to, right, this integral. I am not writing that integral, and consider this function as fz, right. I am not writing that. Okay, I equal to, first one is this bigger arc CR fz dz, then this real interval minus r to 1 minus small r1 fx dx, then again this semicircular arc, and but in negative direction, this is clockwise, minus of cr1 and then fz dz, and now see this small interval 1 plus r1 to 2 minus r2, right, fx dx, again this semicircle, that is cr2, but I should put a minus sign here, right, and fz dz, then this last interval 2 plus r2 to capital R fx dx, and I should write what is my fz. My fz is actually equal to z times e to the power iota z over z square minus 3z plus 2, right. And now, since you know that it goes to 0, why? By Jordan's lemma, right? And on applying, and again, the value of this I is 0. Actually, this I is equal to this integral integrated along this contour C. These are full contour C, right? Full contour, and this contour is not enclosing any poles, so the value of this I will be 0, right? Whenever this shaded region does not enclose any singularity, then the value of this integral is 0. So I will write that here. So 0, and you should know the reason why, equal to 0 plus, and I should write as r1 tends to 0, r2 tends to 0, because these are the radius of two smaller semicircles, right, and capital R should approach to infinity, right, and ultimately if I use r1 to 0, here's that r1, this will become 1 to 2, right, and then here's that 2 to infinity, 1 to 2, 2 to infinity, and before that minus infinity to 1, right, minus infinity to 1, then 1 to 2, then 2 to infinity, means these three integrals evaluated over the part of real line, right, 1, 2 and 3, these will be added up to give you a principal value minus infinity to infinity, right, fx dx, right, and this goes to 0. Okay, that's fine, and we are left with this one and this one, right. Okay, its value should be see this minus pi iota residue of fz, comma, evaluated at this pole, evaluated, see this is cr1, see in picture cr1 is enclosing the singularity z equal to 1, so just be careful at this point, the residue should be evaluated z equal to 1, right. Okay, now we are left with this thing, right, minus pi iota residue of fz evaluated at another pole z equal to 2, because see cr2 is a semicircle and the center is 2, right. Okay, so 1 and 2 are poles. I will evaluate the residue separately. Where is my function? This is my function, right. Or should I bring these two on the same side? So I will get, or principal value of minus infinity to infinity fx dx. Where is my fx? Now I should write the full fx. Fx should be x e to the power iota x over x square minus 3x plus 2 dx, equal to, you can see that these are pi iota, so pi iota should be taken common, and we'll have residue of function evaluated at 1 and plus residue of function evaluated at 2, right. Okay, so pi iota, and if we evaluate the residue of the function at z equal to 1, so this is the function, right. This denominator can be factorized as z minus 1 into z minus 2, because 1 and 2 are the only poles of it, z minus 1 into z minus 2, right? And then you find the residue as z equal to 1, z minus 1 factor will be cancelled out, will be left with z minus 2. So ultimately I will be having 1 multiplied by e to the power iota over minus 1, right, if I am not wrong. And for this I will be having 2 e to the power 2 iota over 1, yeah, okay, fine, right. And now what? Now I will equate the real and imaginary part, right? So I should write it as or principal value of minus infinity to infinity x cos x plus iota sin x over x square minus 3x plus 2 dx. Now equate, what do I need? I need cos. So I will equate real parts, right? Equate real parts. I will get integral, principal value of integral minus infinity to infinity x cos x over x square minus 3x plus 2 dx equal to real part. Okay, I should write real part of this whole thing, yeah, pi iota. First I will write this twice of cos 2 plus iota sin 2, and then minus cos 1 plus iota sin 1, right? Now I will pick up the real part only. I think the real part will be this one, minus 2 sin 2, minus 2 sin 2, and pi should be there, minus 2 pi sin 2, minus 2 pi sin 2, right? And for this we will have minus iota minus plus pi sin 1 plus pi sin 1, if I am not wrong, that will be minus iota, okay, plus pi sin 1, yes. Is it the answer? Yes, right. Principal value of minus infinity to infinity x cos x x square minus 3x plus 2 dx, right? So this is your answer, right? So this is it for this video. In this video we have seen that what happens when pole lies on real axis, right? So we have to do some indentation at that point. We should avoid that pole that lies on real axis, and then the theory is again the same, right? We break the whole contour into 2 or 3 parts or 4 parts, just like in this example, 1 part, 2, 3, 4, 5, 6 parts. So that will depend on the number of poles that will lie on the real axis, and then we apply that Cauchy Residue theorem on the left hand side, right? And for this integral it goes to 0. We use here Jordan's lemma, right, or that estimation principle, and then on approaching r tends to infinity and a small r to 0, we'll get this principal value of the real integral, right? And then we equate the real and imaginary part, right? So this is it for this video. In the next video we'll do something more on complex, right, complex theory. That's it for this video. Thanks.